Alright, ladies and gentlemen, let's go through each and one of these questions together in detail. Yeah? If you look at the first question here, what is a unit of acceleration? You have to recall back acceleration's formula. Acceleration is v minus u over t, right? And the units for velocity is basically in meters per second, whereas time is in seconds. Meters per second divide by second is the same as meters per second multiplied by 1 over second, which will ultimately give you meters per second square, which is obviously C in this question here. Yeah. Second question here, an object is released from rest and falls to earth. During its fall, the object is affected by air resistance. The air resistance eventually reaches a constant value. Which description about successive stages of the motion of the object is correct? A, constant acceleration, then constant deceleration. Constant deceleration, then zero acceleration. Decreasing acceleration, then constant deceleration. Or decreasing acceleration, then zero acceleration. Now, if you think back about an object falling with air resistance, what's going to happen is initially the only thing that acts upon it is gravity, right? And because of gravity, which is somewhere around 10 meters per second square, right? We know that as the speed of the object increases due to gravity, so will the air resistance of the object acting upwards. And in this case here, since the air resistance is eventually building up, causing a decrease in the resultant force downwards, obviously it must be decreasing acceleration lah, right? And then after that, will it decelerate? No, it will not. Why? Because when the upward force is equals to the downward force, it will have zero resultant forces and thus having zero acceleration, yeah guys. Alright, then looking at this next part here, a driving instructor gives a student a sudden order to stop the car in the shortest possible time. Figure 1.1 shows the speed time graph of the motion of the car from the moment the order is given. So you can see here, initially it was moving at somewhere around 18 meters per second. It stopped, the car stopped moving somewhere around 0.9 seconds and then slowly decelerated. Not stopped moving, started decelerating from 0.9 seconds and then eventually stop at 4 seconds here. The order to stop is given at time equals to 0. State the speed of the car at time equals to 0. Then obviously time equals to 0 will be here. The speed will be here. It is absolutely going to be 18 meters per second. Then after that, the second question suggests why the car continues to travel at this speed for 0.9 seconds. Now, if you look at this question here, it says that the instructor gives the sudden order to stop the vehicle. If I look at this graph here, right, this guy, even though he was instructed to stop, right, he had to wait for about 0.9 seconds before he actually started stepping onto the brake and then decelerated the car downwards here. Now, why is it that this question is asking why is it that it took 0.9 seconds for him to finally start stopping the car? This is because all human beings have a reaction time of somewhere around 0.7 seconds. A reaction time of 0.7 seconds, meaning to say, if today I shout at you to stop, you'll take somewhere around 0.7 seconds to process that information, then only your body is going to start stepping onto the brakes, and this is what causes the guy to stop only 0.9 seconds later. So this here is actually going to be a conceptual question. It actually suggests why the car continues to travel at 0.9 seconds is because human reaction time is somewhere around 0.9 seconds in this context here lah. So basically meaning to say he took 0.9 seconds to input the information and his body only started reacting and started braking for this vehicle here. Alright, then after that, calculate the deceleration of the car between 0.9 to 4 seconds here. Acceleration's formula is v minus u over t. Deceleration will be the exact opposite. Deceleration is u minus v over t, u being initial velocity and v being final velocity. So initial velocity, it would have been 18, right? A final velocity obviously is going to be 0. right? Divide by the time taken, which is 4 minus 0.9. From here, just press everything into the calculator and you should get somewhere around 5.8. 5.8 meters per second square, right? 5.8 meters per second square. And finally, they ask you, oh no, not finally, the total distance traveled by the car from 0 seconds, from t equals to 0 seconds. If I'm asked to find the distance in a speed time graph, it is obviously the area under the graph here, right? If I want to do the area under the graph, I could either find it through this rectangle here and then this triangle here, or I could just use this other shape formula. What's this shape called again? Parallelogram. Is it called a parallelogram? Trapezium lah, or whatever this shape is called, right? This here is going to be 0.9. Here would have been a total of 4. Here would have been a total of 8. So it's going, the formula is supposed to be a plus b divided by 2 times c. This is going to be your a, this is going to be your b, divided by 2 times with your c. So in this case here, it will be 0.9 plus 4 divided by 2 multiplied by your 18. In this case here, it will be 4.9 divided by 2 times with 18. You'll get a total distance of 44.1 meters. 44.1 meters. Describe and explain a danger to a driver of not wearing a safety belt during a sudden stop. This one here is just going to be a conceptual question. If you ever not wear your seatbelt and you experience a sudden stop before, what's going to happen is the momentum from the car will be transferred to your body and you will start flying off the window, smashing your head and injuring yourself. So describe and explain. Momentum from the car will be transferred to the driver, cause it during the sudden stop. The driver will be sent flying forward, smashing his head against the windscreen and injuring himself. Alright, momentum from the car will be transferred to the driver. During the sudden stop, the driver will be sent flying forward, smashing his head against the windscreen and injuring himself. Okay, so this will be the part 1 of motion time graph. Let's proceed to part 2. Okay, looking at part 2 here, this is actually a very interesting question. The question states that the speed time graph shown is for a car moving in a straight line. You can see that the car moved at probably somewhere around 3 meters per second, started accelerating, and then started decelerating, and then finally going back into speed equals to 0 here. In this question here, they ask, what is the acceleration of the car when time is equals to 40 seconds? Now, a lot of students, they have this misconception when dealing with this question. They will think that, okay, 40 seconds, I'll find the final velocity here, I'll find the initial velocity here, which is somewhere around 15, this will be somewhere around 3, and I'll find the total time taken for this, and the working they will give me is going to be something like 15 minus 3 divided by 40, which will lead them to circle B as the answer in this question here. But in reality, this is not going to be the case, because if B was the answer, the line would have looked something like this instead. The line, oh god, the line, oh god, the line would have looked something like this instead. It will be something like this instead. And you know for a fact that this is definitely not going to be the case, because the graph is obviously curving at this point, right? So what you have to do is you have to understand that if the question gives you a specific time, like 40 seconds here, you are actually expected to draw the tangent of the graph at exactly 40 seconds here, which is going to be somewhere around here. Drawing a tangent will give you this line here, which indicates that it has a 0 gradient, ultimately indicating that acceleration is 0. Now, how do I also know that this is actually going to be zero acceleration? From here, you can see that the speed is increasing, right? The speed increasing, meaning to say this part here, it was accelerating. And this part here, it is basically going downwards, right, with a negative gradient, meaning to say it is actually decelerating. In between accelerating and decelerating, the car must come to a point where the acceleration was zero. Only then can it start going deceleration. So answer is obviously A in this question, yeah. And question number 2 is also one of my favorites. Two runners take part in a race. The graph shows how the speed of each runner changes with time, runner 1 and runner 2. You can see that runner 1 has a constant acceleration and runner 2 has a decreasing acceleration based on the gradient. So what does the graph show about the runner at time equals to t? Both runners are moving at the same speed. This is definitely possible because at time equals to t, runner A and runner B are moving at exactly this time. Runner 1 has zero acceleration. This is absolutely impossible because this runner here is actually having a constant gradient indicating constant acceleration. Runner 1 is overtaking runner 2. This is not possible as well because if runner 1 was taking over runner 2, the distance covered by the runner 1 would have been greater than the distance covered than runner 2. But in this case here, you can see that area under the graph for runner 2 is actually higher, indicating that runner 2 is further away than runner 1. And finally, runner 2 is slowing down. No, runner 2 is not slowing down. Runner 2, if anything, is actually still speeding up, just that with a decreasing rate. And that is why answer is supposed to be A in this question here, yeah. Then looking at question number 3, a car travels along a straight road. The speed time graph for this journey is shown, during which labeled part of the journey is the resultant force on the car 0. In order for the resultant force to be 0, the speed must no longer be increasing. In other words, zero acceleration. So answer is obviously going to be B in this case here. A large stone is dropped from a bridge into a river. Air resistance can be ignored. Which row describes the acceleration and the speed of the stone as it falls? If air resistance is ignored today, the only thing that acts on the object is going to be gravitational acceleration. So from here, I know for a fact that the acceleration of the stone is definitely going to be constant. It is never going to increase because gravity is not increasing on the object. And if my gravity is increasing because of constant acceleration, if my acceleration is constant due to gravity, my speed is definitely going to increase here. So answer is going to be boy. And question number 5 here, an object moves at a constant speed for some time, then begins to accelerate. Which distant time graph shows this motion? Now, if you recall back a distance time graph, the gradient of the graph indicates that it is the speed, right? Meaning to say, in order for it to accelerate, I must have increasing speed, also known as increasing gradient. Looking at this here, has zero gradient, zero speed, constant gradient, constant speed, constant gradient, increasing gradient, means to say constant speed, then increasing speed. Then here it's just all the way increasing speed, in other words all the way acceleration. But in this question here, since it has to move at a constant speed for some time, then begin to accelerate, then to have increasing acceleration, answer should be C in this question here, right? Then moving on to the next part here, a bus travels at a constant speed, it stops for a short time, then travels at a higher constant speed. It moves at a constant speed, stops for a short time, then travels at a higher constant speed. Using the axis in figure 1.1, draw a distance time graph for this bus journey. Yet again, a distance time graph, the gradient is supposed to represent the speed. If I have constant speed, I should have constant gradient. It stops for a short time means to say zero speed, zero gradient. It should be a straight line here, right? And then higher constant speed, which should have a higher gradient here. So you're supposed to end up with this, and you'll get your free 3 marks here. All right. Then after that, a lift elevator starts from rest at the ground of a building. Figure 1.2 is the speed time graph for the motion of the lift to the top of the floor of the building. So initially it starts with 0, it moves with a constant acceleration all the way until it's 3.2, is it? Yeah, it's 3.2 here. Or it will be 3.2 here. Then after that, this point of time would have been 7.5. This here would have been 20 and 3.2. And this here will be 0. Okay. Use the graph to determine the distance from the ground floor to the top floor of the building. If I'm asked to find the distance in a speed time graph, I'm obviously supposed to look for the area under the graph. In this case here, this will be my A, 25. This will be my B, which is 20 minus 7.5, a total of 12.5. And my C should be 3.2. Writing everything into calculation, it will be something like 12.5 plus 25 divided by 2 multiplied by 3.2. Press that into the calculator. You'll get a total distance of 60 meters. You'll get a total distance of 60 meters here. Right? Then, second part. An object is moving in a straight line at a constant speed. A force is applied to the object. State the possible changes in the motion of the object. If today an object is moving at a constant speed forward, once I apply a force, I could change its direction. If I apply a force here, I could decelerate it. If I apply a force here, I could accelerate it. So you can write either one of it is definitely acceptable. Number one, accelerate the object. Number two, decelerate the object. Oh god, single C. And number three, it could change the direction of the object. Okay, either two is definitely acceptable because it's 2 marks here, guys. Alright, then moving on to the next part here. Figure 1.1 shows a skier taking part in a speed competition. The winner of the competition has the highest average speed over the 100 meters section as shown in figure 1. This guy should fly fastest at this specific section here. The skier starts from rest, indicating that the initial velocity is 0 and has a constant acceleration. He reaches a speed of 60 meters per second. This is obviously a final velocity in a time frame of 16 seconds. Calculate the skier's acceleration. Straightforward, A equals to V minus U over T here, which in this case will be 60 minus 0 divided by 16. Press that into the calculator. You're going to get an acceleration of 3.75 meters per second square. Now, the next part here, over the length of the 100 meters, which is your distance, the time recorded was 1.85 seconds, which is your time. Calculate the skier's average speed. Now, if you ever see this word average speed, you should recall that speed's formula is still distance over time. Average speed is total distance over total time, which is in this case 100 meters divided by 1.85 seconds. Press that into the calculator and you'll get somewhere around 54.1 meters per second. 54.1 meters per second here. And finally, they ask you to suggest why the skier bends his body as shown in figure 1.1. There are two specific reasons why he bends his body. And number one, as he bends his body, his center of gravity is lower, so he is more stable. Or number two, when he bends his body, he's actually exposing less surface area, so he experiences less air resistance. Either one you write is definitely acceptable. To lower his body so the center of mass is closer to the ground, making him more stable, or to reduce surface area of his body to have less air resistance. Okay, either one is definitely acceptable. Okay, moving on to the next set of questions here. The graph shows how the distance travels by a vehicle changes with time. Yet again, a distance time graph. this is going to be constant speed, 0 speed, and constant speed yet again. Constant speed, 0 speed, and also constant speed yet again. Alright, a stone falls freely from the top of a cliff. Air resistance may be ignored. Which graph shows how the acceleration of the stone varies with time? Now, the key word here is that the air resistance may be ignored. If air resistance is ignored, the only thing that acts upon the object is going to be gravity. By right, the speed of the object is going to constantly increase. But if you notice at these answers here, it's actually not a speed time graph. All of it is a acceleration time graph. And if they are all acceleration time graphs, and I mentioned that the acceleration of the object is due to gravity, which is constant, the answer should be donkey here. A lot of students, they have a high tendency to circle this as the answer as soon as they see air resistance may be ignored. Please be careful of the axis given. The information from the axis given is very, very important. Alright, then after that, proceeding on to question number 3. A car travels along a horizontal road in a straight line. The driver presses the accelerator to increase the speed of the car. The speed time graph for the car is shown. This guy is basically increasing his speed from 20 to 30 in a span of 20 seconds. What is the acceleration of the car? Straightforward. Yet again, A is equals to V minus U over T. In this case here, it will be 30 minus 20 divided by this time here, which is 20. Obviously, your acceleration is going to be 0.5 meters per second. Very straightforward, nothing to explain. Question number 4. The speed time graph for an object shown. Speed increase, accelerating, constant speed, deceleration. Below are 4 statements about the acceleration of the object. Which statement is correct? The acceleration in the first 5 seconds is given as area of P. No, definitely not true. Area under a speed time graph is the distance. So this is out of the question. The acceleration increases between W and X. The acceleration does not increase. The speed increases. Right, so this is out of the question as well. The acceleration is negative between Y and Z. That could be possible since it has deceleration. The deceleration between Y and Z is 20 divided by 15. Definitely not. Divided by 25, not possible because the time should be 10 instead. This should be 10. Answer is C in this case here. The speed time graph for an object shown. Same thing. Below are 4 statements about the acceleration of the object. Which statement is true? The acceleration in the first 10 seconds is 10 divided by 10 meters per second squared. Oh, this is possible. It's 10 divided by 10, the acceleration. The acceleration increases between W and X. Yet again, the acceleration does not increase. The speed increases. The acceleration decreases between Y and Z. If you have decreasing acceleration, you should have a curving graph like this that has a decreasing gradient. So it's not this as well. It's not this, not this. The deceleration between Y and Z is 10 divided by 50. No, it should be 10 divided by 20 here. So answer is going to be A. Alright. Moving on to the next question here. An astronaut on the moon drops a feather from rest off the top of a small cliff. The acceleration due to gravity on the moon is 1.6 meters per second squared. This is going to be acceleration. There is no air on the moon, so there is no air resistance as well. Yeah, the feather falls for 4.5 seconds before it hits the ground. Figure 1.1, draw the speed time graph for the falling feather. Now, if they say that the acceleration is 1.6 meters per second squared, it means to say every second that goes by, the speed will increase by 1.6. Now, there are 2 ways to attempt this question. Number 1, you could either scroll in real hard and you'll find that this is 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6. You have this one line here drawn. You have this one line here drawn all the way upwards until it is somewhere around 4.5. Wait, go up, go up, go up. 4.5, which is somewhere around here lah. 1, 2, 3, 4, 5. Here. Yeah, be somewhere around here. Or alternatively, you could do the acceleration formula, which is going to be a equals to v minus u over t. In this case here, I'm looking for the final velocity, right? And I know that the initial velocity is 0. So it's basically at is equals to v minus u. In this case here, it will be 1.6 times 4.5 is equals to v minus 0. V would have been 1.6 times 4.5. You would still have gotten somewhere around 7.2, which is correct also as 6.2, 6.4, 6.6, 6.8, 7, and 7.2. Oh, here. It should be continued. 1, 2, 3, 4, 5. Yeah, if you draw in a straight line, it would have been correct. But anyhow, it's supposed to end somewhere around 7.2, yeah. It should end somewhere around 7.2, which is, yeah, somewhere around here. Okay, just draw your straight line properly. Determine the distance fallen by the feather. The distance is obviously going to be the area under the graph here. In this case, it will be 7.2, here will be 4.5. Half times 7.2 times 4.5, press that into the calculator. You'll get a total distance of 16.2 meters here, 16.2 meters. On figure 1.2, sketch the shape of a speed time graph for the same feather falling. This guy here has a constant increase in the speed. Oh, sorry, this is not related. On figure 1.2, sketch on Earth. On Earth where there is air resistance, guys. If there is air resistance, it means to say the object will eventually have the upward force equals to the downward force, and thus you should draw a graph that is curving and eventually flat lines. It should be something like this here, right? This flat line is where the terminal velocity occurs. Terminal velocity can only occur when the upward force is equals to your downward force here, guys. And finally, explain the difference between speed and velocity. Include words like vectors and scalar. In this case here, speed is a scalar quantity. It only has magnitude. Velocity is a vector quantity. It has magnitude and also direction. Okay. Next. Figure 1.1 shows a student traveling down a hill in an unpowered vehicle. Figure 1.2 is part of a speed time graph for the vehicle traveling down the hill. You can notice that from A to B it is actually one straight line, then B onwards it is actually curving. This indicates that it has constant acceleration here. Decreasing gradient means to say decreasing acceleration. Decreasing acceleration is not the same as deceleration. Deceleration is for the speed to decrease, but you'll notice that at no point in time has the speed actually decreased. So decreasing acceleration is not the same as deceleration. Look at this question here. State how the graph shows that the acceleration is constant between A and B. Very straightforward. It has a constant gradient between A and B. Very easy. After that, calculate the acceleration between A and B. The acceleration should be A equals to V minus U over T. In this case here, the final velocity will be 4 minus 0 divided by a total time of 2. You're supposed to get 2 meters per second square. Alright, then after that, describe how the acceleration changes from B to C. You can see that the gradient decreases, indicating that the acceleration that you have decreasing acceleration. And finally, the bane of all students, Using figure 1.2 to obtain an approximate value for the distance traveled by the vehicle in the first 10 seconds of the graph. Now if I want to find the distance traveled in a normal graph, usually I'll just find the area here, find the area here, and then I'll be able to add them both together and find the total distance traveled. But you notice that in this question here, the graph actually curves. There is no way for you to find the area under a curved graph unless you're doing the at-max formula dy dx. But in this case here, what you can do is you can do approximate values. So what you're expected to do is you're supposed to separate this graph into many sections. The first section being this part here. We'll call this section A. Oh God, what's going on? Then we'll separate this part into section B. And we'll separate this part into section C, this part into section D, and finally this part into section E. A, B, C, D, E, right? So you're supposed to separate these in different sections. The first section being here to here. The second section being here to here. The third section being here to here. The final section being here to here as well. Okay, you're supposed to shape it into approximate shapes that you know, which is going to be a trapezium. And you're going to ignore the rest of it. Okay, so if you ignore the rest of it, first things first, what's this unit here? This is the coordinate here is 2, 4. The coordinate here will be 4, 6.3. The coordinates here will be 6, 7.2. And the coordinates here will be 8, 7.9. Here will be 8 lah. 8, sorry, 10, 8. So if I want to find the area here, it's very straightforward. It will be 2 times 4 divided by half. 2 times 4 divided by half, which is obviously going to be 4. This one here will be A plus B divided by 2 times C. In this case here, it will be 4 plus 6.3 divided by 2 times with C, which is going to be 10.3 divided by 2 times 2. Oh, it's straight away just going to be 10.3. This one here will be 6.3 plus 7.2 divided by 2 times 2, which is going to be 13.5. This part here will be 7.2 plus 7.9 divided by 2 times 2, which is going to be 15.1, and finally this part here is 7.9 plus 8 divided by 2 times with 2 as well, which in this case here will be 15.9 plus all of them together, 4 plus 10.3 plus 13.5 plus 15.1 plus 15.9. You'll get approximate value of 58.8 meters. Okay, you're supposed to use approximate values. You'll neglect all this part here. You're going to ignore all this part here because you're just supposed to find the approximate values, right? 58.8 meters. Let's do this last part here. A diver in the sea uses a breathing apparatus which releases gas bubbles. Figure 1.1 shows the gas bubbles rising to the surface. The gas bubble starts from rest initial velocity at first, and they move upwards with a constant acceleration. figure 1.2 is an incomplete speed time graph for one of the bubbles from 0 to 10 seconds here. Using figure 1, determine acceleration of bubble for the first 2 seconds is supposed to be a equals to v minus u over t. In this case here, the velocity would have been 0.5 minus 0 divided by 2, which is going to give you a total of 0.25 meters per second square. Right? After 2 seconds, the acceleration of the bubble decreases gradually. The acceleration decreases, not the speed. The acceleration decreases gradually until it reaches 10. Its acceleration is 0. Complete figure 1.2 by sketching a possible continuation of the speed time graph. It's supposed to have decreasing acceleration, in other words, decreasing gradient. And eventually it flatlines to become 0 because it's going to have 0 acceleration. So what you're supposed to do is you're supposed to curve this graph and eventually give it a flat line to indicate that the acceleration is 0. And finally, state the name given to a negative acceleration. The negative acceleration is known as deceleration. Very straightforward. Okay.